Hello friends, in this video we will be discussing the Astablemultivibrator using comparison. So before entering to the Astablemultivibrator, let us see what is trimerizing. So because of the low price and the use of use and the stability of the IC, the 555 IC timing is almost all the projects, and this provides timetables as an oscillator and a circuit property. So this is an integrated circuit used for many of applications as a premium power, and it was introduced in 1971 by the American company called Synaptics. And let us see the internal block diagram of IC55. This is the block diagram, and this is the block diagram. And here you can see it's a 8-pin dual inline package, and the internal circuit of 555 IC consists of 24 transistors and so many resistors and capacitors. And as a block diagram, we can represent the 555 IC as like this. So here you can see it consists of 3 5K resistors. That's why we name 555 IC timer, and which provides it acts as a voltage divider for this circuit and provides the bias voltage for the lower and the upper comparator. The bias voltage for the lower comparator, for the comparator 2 in this figure, is 1/3 VCC, and the bias voltage for the upper comparator is 2/3 VCC, and the output of these two comparators is connected to the RS flip-flop input, R and S input respectively of comparator 1 and comparator 2, and the output Q bar is, remember, Q bar is connected to the circuit output through an inverter. So that means if the Q bar output is 0, the circuit output or the IC output will be 1. And also the output is also tied to the collector of this transistor Q2 for providing reset. And if pin number 1 is ground, pin number 2 is a trigger for the lower comparator. If we want to give external trigger, this pin can be utilized. And the 3 is the output pin, and 4 because it's a reset, and the 5th pin is the control voltage. If you want to change the bias voltage of the comparator 1, the 5th pin can be utilized, and for setting the threshold for the comparator 1, the 6th pin can be utilized. And normally we are connecting the capacitor to this 7th pin, and the 7th pin provides the discharge path through this Q1, and 8 is obviously the VCC for circuit operation. And the 555 IC generally operates in 3 modes: astable mode, monostable mode, and unstable mode. In the astable mode, no stable state. It has only 2 quasi-stable states. That's why you need astable mode. There is no stable state, and that means the output of the astable multivibrator toggles between high and low. And the astable mode of the 555 IC can be used as a clock or a square wave output for other circuits. And the next mode of operation is monostable mode. It has only 1 stable state, and it requires external trigger for changing the output from stable state to the quasi-stable state. And the output of the monostable state remains in the quasi-stable state for a particular time period, and it changes automatically to the stable state and usually And the third mode of operation is bistable mode. It has 2 stable states. It requires an external trigger for changing both the output Now let us see the stable multivibrator using profile IC. And the circuit diagram of stable multivibrator using profile IC is shown here. It consists of two resistors and two capacitors are connected to the external to this profile IC. And here R1, R2 and C forms a series network between the VCC and ground, and the port and the pin of this IC are not being used, so the port pin is connected to the VCC or pulled up, and the fixed pin is connected to the ground by using a 0.01 microfarad capacitor, and the trigger and the threshold pin is tied together and connected to the point where C1 and R2 meet to operate the circuit as a clear-wave oscillator or square wave generator. So during each cycle, the capacitor charges up through with resistor R1 and R2 and discharges itself only through the resistor R2 and to the internal circuit. So let us look into the internal circuit of this IC. So this will be internal circuit along the external components. Here you can see the circuit here. So in the initial stage, that means in the standby mode, the voltage across this capacitor C1 is lesser than 1 by 3 VCC. So the voltage across this capacitor is usually lesser than 1 by 3 VCC or the bias voltage of this lower comparator. As a result, the output of this upper comparator becomes 1. So the drop is set, that means Q becomes 1 and Q bar becomes 0. So the output of this IC becomes 1 because of the inverter circuit. And while the Q1 transistor is switched off because of this Q bar is 0. So as a result, the capacitor C1 charges through R1 and R2 towards this VCC. So you can see initially from this graph, you can see initially the output is 1 and the capacitor charges towards the VCC, and whenever the charge is equal to 2 by 3 VCC of the voltage, the upper comparator output becomes 1 and the RS flip-flop is reset. That means Q bar becomes 1. As a result, the output of the ML circuit is at 0.23 is 0, and meanwhile the Q1 transistor switched on. So the capacitor from its maximum value of 2 by 3 VCC starts discharging to the R2 and this Q1 to ground. So whenever the voltage after time period of T2, the voltage across this capacitor is slightly lower than 1 by 3 VCC. Again, the lower comparator output becomes 1 and the stop is set, the power becomes 0 and the output becomes 1. And the process repeats. This is how the 555 IC timer operates in a stable mode of operation. So the capacitor charges to 2 by 3 VCC through R1 and R2. So that time period is determined by equation points 693 into R1 plus R2 into C, and the discharge time can be calculated using the equation 0.693 into R2 into C. So as we discussed, during the charging time, both R1 and R2 and C are in the picture, and while discharging, the capacitor voltage discharges through this R2 only. Right, that's why the equation for P2 is 0.693 R2 into C. So here you can see that P1 is the charging time and P2 is the discharging time. So this results because the charging and discharging depending upon the capacitor voltage, this results in an output waveform whose voltage level is approximately equal to VCC minus 1.50. The output on and off time periods are defined by the capacitor and resistor combination as we discussed now, and the individual time for charging is P1 and for charging is P2 can be calculated using this equation. P1 equal to 0.693 into R1 plus R2 into C, and P2 is C, where R is in the ohm and C is in farad. And the total time period can be calculated by adding these two time periods, P1 and P2, which is equal to 0.693 into R1 plus 2R2 into C. And if we take 1 upon the total time period T, we will get the frequency of oscillation. So the circuit frequency is given by 1.4 divided by R1 plus 2R2 into C. And another important factor in case of this stable multivibrator is its duty cycle. What is the duty cycle? The duty cycle is the ratio of on time divided by the total time period. So duty cycle equal to T on upon T of plus T of, which is R1 plus R2 and R1 plus 2R. So normally the duty cycle is represented in percentage, since there is a unit for that. And if what happens is R1 equal to R, is it provide duty cycle of 50%? Yes, obviously not. We know here duty cycle is R1 plus R2 by R1 plus R2. So it provides the duty cycle will be 2:1, so that means 66% on time and 23% off time. So this is a stable multivibrator, and let us recap the working of a stable multivibrator using 2.5 IC. So when initially the power is turned on, it triggers in voltage. This is the trigger in voltage. The number 2 is less than VCC by 2. So the power comparator output is high and sets the trip off, and the output of the profile is high. This makes the transistor Q1 off. We make this Q1 off, and the capacitor charges through R1 and R. Whenever the capacitor voltage is greater than 2 by 3 VCC, that means when the voltage of non-inverting and or if the number 6 becomes higher than the inverting and of the comparator, this means this apparent under the output 1 and its reset is the clock and Q bar becomes 0, 1 and the output becomes 0. Since the output is the clock bar. So as a result, Q bar is 1 and the transistor Q1 becomes on. So there is a discharge path for this capacitor voltage. So R2 and Q1 is discharges as the output is. So as soon as the output of 555 get low, which Q bar is 1 and the transistor Q1 becomes on and short the capacitor Q1 to the ground. So the capacitor C1 starts discharging to the ground. We will discharge in 7M resistor. After this is the waveform of output and capacitor charging and discharge. So let us derive the charging time T1 and charging time T2. So for that, let us write the voltage across the capacitor as VCC equal to the final value plus initial value minus final value equals to minus T by R1 plus R2 C, and here you can see from this figure the initial value is VCC times 3 and the final is VCC because the capacitor is charging towards VCC. So let us substitute VI and VN here. So VC P1 equal to, why this P1? Because we are calculating the charging time P1 to P1. So VC P1 equal to VCC plus VCC on substituting the initial and final value we get minus VCC by 3 equal to minus 3 VCC by 3 minus P1. So this gives, on simplifying this gives P1 equal to 0.693 into R1 plus R2 into C. Right, this is P1. Similarly, we can calculate or derive the charging time P2. So once again, let us write VCP equal to VF plus VL minus VF to the raised to minus P2 by R2 C. Because while discharging, the discharging time A is P2, here you can see is P2, right? So here you can see the discharging time is P2. So here the initial voltage is 2 by 3 VCC while discharging, right? So at this point, the voltage is VCC by 3 and the final value is discharges towards 0. That's why the final value is 0. So substitute these values here. VC into P1 equal to 0 plus 2 by 3 minus P2 by R2C. While discharging, there is only R2 in part. Right, that's why here P2 by R2C. So on solving this equation for P2, we get P2 as 0.693 into R2C. So if we add these two voltages, we get the total time period as T equal to T1 plus T2, which gives the total time period as 0.693 into R1 plus R2C. And from the final time period or the total time period, we can calculate the frequency of the oscillation, which is 1 upon T, which is equal to 1.44 divided by R1 plus R2 into C, and the duty cycle can be found as the number of T plus T. Right. So this is all about Astablemultivibrator Usin. And I would like to give you videos assignment. So let us try so that we will get or not. This is about three equations we can calculate. Please note down this assignment. The answer is in second. It is 40 meters. An stable oscillator is constructed using the following components: harmonic component load, transmitter load, and capacitor equipment, and calculate the output frequency from the specified oscillator and the specified clock. So for that, first you need to find T1 and then T2 and then find total time period, and with the basic equation of frequency equal 1 by 2, we can calculate the frequency, and with the value of R1, R2 and C, we can calculate the cycle. So hope all of you understand. Thank you.